Faster than light travel, wormholes, warp drives, anti-gravity. How is it that the cool physics stuff is always that which doesn't exist? Or maybe physicists are just wrong about what exists. A paper which just appeared last week says that tachyons, that are particles which move faster than the speed of light, might exist after all. And I want to explain why that isn't as crazy as it sounds and what's it got to do with wormholes and warp drives. This video comes with a quiz that lets you check how much you remember. The word tachyon is Greek for a fast thing, and indeed they'd be very fast, faster than anything we've ever seen, faster than light itself. At first this seems possible because, contrary to popular belief, Einstein's theories do not rule out faster than light travel. It's just that we don't know a way to accelerate an object from below to above the speed of light. The speed of light is a barrier, really, rather than a limit. I explained this in more detail in an earlier video. Nevertheless, physicists believe that nothing can move faster than light. It's for two reasons. One is that such particles can appear as if they go back in time, and the other one is that they can have negative energy. Also, they say. To understand why they say that, I'm afraid I'll have to draw one of these diagrams, though by now you've probably become used to them. This is a space-time diagram with time on the notes vertical axis and space on the horizontal. We draw the speed of light by convention at a 45-degree angle. So if you have a particle going on this line that's slower than the speed of light, if it goes on this line, it'll be faster than the speed of light. The line which the particle moves on is called the world line. The issue with tachyons going back in time now comes about as follows. A particle which moves faster than the speed of light would by some observers been seen as a particle that goes back in time. This is because if you think that this is what you see, a particle goes forward in time faster than the speed of light, then an observer who moves relative to you might actually see this, a particle going backward in time. Note, though, that to make this point, I had to put an arrow on the line. I'll come back to this in a moment. The issue with the negative energy of tachyons is really the same problem. This is because instead of taking a space and time diagram, we could use energy and momentum. For a particle that moves at a constant velocity, the momentum just goes in the same direction as the world line. So, by the same argument as previously, it can go backward in the energy direction, which means it has a negative energy. And then, so the argument goes, that can't exist, because if one could have particles of negative energy, then one could make pairs of particles of positive and negative energy out of nothing. And our entire universe would have ripped itself apart long ago, probably out of laughter, because I'd say this argument is obviously wrong. It's because particles don't go forwards or backwards in time. That's a physically meaningless statement. Particles are in space somewhere at some time. That's it. They don't move in time. That doesn't mean anything. This was why, to even make sense of this, I had to put an arrow on the world line. As I just said a week ago, that a particle goes back in time to the left means the same as that a particle goes forward in time to the right. If you think that one of them has negative energy and the other positive energy, you obviously did something wrong. And that brings me to the new paper, because that's basically what they do, just with maths rather than words. They say that we can solve the problem with negative energy by taking into account that we could always interpret a particle as either going forward or going backward in time. So to any particle they assign a sort of double state, one going forward and one going backward in time. And the energy that the particle has is then by definition the positive one. That sounds very obvious, but mathematically it's a new idea. Well, kind of. Because there's an interpretation of quantum mechanics which works similar to that. It's called the two-state vector formalism. According to this interpretation, if you want to correctly describe what goes on with a quantum particle, you both have to ask how it'd behave forward in time and backward in time. So Schrödinger's cat isn't only dead and alive, it's also dying and coming back from the dead. If that made no sense, don't worry. If you calculate anything using this interpretation, it comes out to be the same as normal quantum mechanics. So what's the point then? Well, the new paper suggests that the point is that it can also deal with faster than light travel. What's this to do with wormholes and warp drives and anti-gravity? The connection is that these three require negative energies, and that's the reason why physicists will tell you that they can't exist. The new paper casts doubts on physicists' reasons to dismiss them. Einstein is a little skeptical of all this faster-than-light business, but personally I think this deserves much more attention. It's because I think the reason for the Fermi paradox, why we haven't heard of extraterrestrials if they exist, is that they communicate and travel faster than light, and we haven't yet figured out how to do it. I can't wait for Amazon to make my tachyonic home deliveries. Maybe they even arrive before I've made the order. Nuclear power is currently seeing a renaissance in big parts of the world, but many of the newly planned nuclear power plants use a fuel that's much more enriched in radioactive compounds than the currently used one. Some experts are raising concerns about it. Let's have a look. Small modular reactors have recently gained popularity. The idea is that these reactors will be small enough to be transported so they can be produced in a factory and then shipped to wherever you want them. This could make the construction of nuclear power plants faster and cheaper. Whether that'll work out remains to be seen, but the small reactor boom has greatly increased demand for a special type of fuel called HALEU. That might sound like a greeting for nuclear engineers. Hey Lou, how are you doing? But it stands for high assay low enriched uranium. What's that? Well, natural uranium has about 0.7% of the radioactive compound that's uranium-235. All the rest is almost all uranium-238. The currently most widely used nuclear reactor types that are pressurized water reactors use what's called low-enriched uranium. That's more than the natural level but below 5% of uranium-235. Then there's HALEU, which has anything between 5 and 20%. And then there is high-enriched uranium that can be used for nuclear weapons, which is anything above 90%. HALEU is becoming popular as a fuel not just because it's necessary to build smaller reactors, but also because it's more efficient in using the fissile materials and because it generates less waste. Unfortunately, the biggest exporter of enriched uranium is currently Russia, and they have recently become somewhat unpopular. This is why the United States are now building their own enrichment facilities, and also the UK has proudly announced a plan to do so. So HALEU facilities are becoming more numerous, and that has brought up safety concerns. Most notably, there was recently a comment published in Science magazine whose authors claimed that using HALEU much increases the risk of nuclear proliferation. They write, HALEU above about 20% uranium-235 could be used to make a practical weapon. This sounds alarming, but it's misleading. First, it's not like you need to reach a certain level of enrichment to get a nuclear chain reaction. It's just that the lower the enrichment, the more of the material you need, and that gets impractical quickly. If you have weapon-grade uranium, you need something like 55 kilograms or so to get a chain reaction. If you have 20% enriched uranium, you'd need something like 500 kilograms. With 15%, you need a ton of it, and so on. You can do it theoretically, but practical is something else. Even if someone would manage to legally acquire a ton of HALEU, what would they do with it? The biggest difficulty in building the first atomic bombs was to get the material to detonate efficiently, and that required a lot of tinkering to get the fissile material to join at the right moment in exactly the right configuration. Just exactly how it works is today the most top secret of all top secrets, and that was with highly enriched uranium or plutonium. If you have a ton of material rather than 50 kilograms, that isn't going to make it easier. Robert Hayes, professor for nuclear engineering at North Carolina State University, explains the problem as follows. Until fissile concentrations get very, very high, the ability to rapidly increase reactivity enough to produce a viable nuclear yield is extremely difficult. The whole process is continually trying to disassemble itself through thermal expansion and requisite phase change, which is always the case in an inadvertent criticality event. To do better than can be done with high explosives may be possible, but if the superpowers can't do it, I really have no concern that others will do better. In an interview with Verge, Charles Forsberg from MIT said similarly, unless they're a whole lot better than I am and the colleagues I work with, a subnational group like a terrorist group doesn't have a chance. Basically, they're saying that building a nuclear bomb from HALEU is more difficult than enriching uranium and building a bomb with that. And if you're enriching already, why steal HALEU? That makes no sense. And that's leaving aside that carrying off a ton of material unnoticed isn't all that easy, and a nuclear power plant doesn't have that much of the stuff lying around to begin with. This is why most experts consider the risk increase from HALEU to be moderate for what nuclear bombs are concerned. But there are other problems with the stuff. One is the issue of dirty bombs, an explosive device that sprays radioactive compounds around rather than causing a chain reaction. It's technically not difficult to build and could contaminate large areas. The risk of someone acquiring enough radioactive material to build one generally increases with more nuclear facilities, including HALEU production sites. The other problem is that some countries might use HALEU production as a pretense to produce highly enriched uranium. So yes, radioactive compounds are dangerous and HALEU needs high safety standards. Everyone agrees on that anyway. But claiming that one could build a nuclear bomb with it is stretching the truth. And in any case, who wouldn't like to have a three-eyed fish? We haven't talked about black holes for a while, but today I have a very neat paper about supermassive black holes and what they might have to do with dark matter. Let's have a look. Supermassive black holes are the most mysterious objects in the universe, according to my humble opinion. Up second is the thing that I found in the drawer last week, which was certainly there for a reason, but damned if I know what it is. The issue with supermassive black holes is the same. Astrophysicists don't understand why they're there. Because according to the currently most widely accepted model for the universe, black holes can't grow fast enough to get as big as the ones we observe. We know that supermassive black holes can have masses up to several billion times the mass of our Sun. They sit in the centers of most galaxies, and some of them accrete a lot of matter. This infalling matter heats up and spits out gas and radiation. That's what we call an active galactic nucleus. But what happens if two galaxies with supermassive black holes collide and merge? Then you have a bigger galaxy with two black holes. The problem is we observe very few galaxies with such binary supermassive black holes. So it seems that the black holes merge too. But how do they merge? You might think that this would happen the same way that stellar mass black holes grow. They orbit around each other. That emits gravitational waves. The gravitational waves carry away energy, so the black holes spiral into each other and eventually merge. But that doesn't work for supermassive black holes. Because they are larger, the wavelength of the gravitational waves are much larger, and the energy that's carried away is much smaller. For a pair of supermassive black holes to merge, that'd take way longer than the age of the universe. So how do they ever get together? As long as they're quite far away from each other, they lose energy by colliding with stars or being dragged down by gas and so on. Basically, there is other stuff and that creates friction. But once they are only a few light years apart, there isn't much left that could create friction. So they just settle on a stable orbit around each other rather than merging. The distance at which this happens is about a parsec, and so astrophysicists dubbed it the final parsec problem, that it takes seemingly forever for the two to get together. I think it should have been called the Bridget Jones problem. In any case, the authors of the new paper say there's a simple solution. It's friction from dark matter. You see, astrophysicists think that dark matter is distributed in and around galaxies in what's often called the dark matter halo. The density of dark matter is the highest in the center of the galaxy, so where the supermassive black holes sit. Dark matter, like all matter, generally creates what's known as dynamical friction. That's just its gravitational pull. However, that friction isn't high enough to get the black holes to merge. But the authors of the new paper say that if the dark matter interacts with itself, then that'd cause much more friction and make the supermassive black holes merge much faster. Even better, they say that this would leave an observable imprint in the gravitational wave spectrum from black hole mergers. The gravitational wave spectrum in this frequency range has not been well studied, but there have recently been some tentative measurements from pulsar timing arrays. For this method, one uses the timing of pulsars that are neutron stars which emit particle beams. They rotate, and so this particle beam reaches us with an extremely reliable period. If you measure distortions in the pulsar signals from different directions, that can tell you whether gravitational waves stretch the space in between. This method is sensitive exactly in the frequency range of gravitational waves that one expects from supermassive black hole mergers. The authors of the new paper say that the results of the preliminary measurements speak for their idea because it suppresses the power at low frequencies. But there is a problem. That dark matter creates some sort of friction might help to get black holes to merge, but it would cause other problems. It would, for example, also slow down small satellite galaxies that go around larger galaxies because the dark matter halo extends until there. The Milky Way too has dozens of these small satellite galaxies, and they move too fast to be compatible with the dark matter halo. This is a problem already with dynamical friction, but if the dark matter is self-interacting, I suspect that'll just make the discrepancy with observations worse. Though I'm just guessing here because they don't discuss this in the paper. In any case, these are exciting times because one way or another, the observations from the pulsar timing arrays can tell us how the supermassive black holes spiral into each other. So maybe physicists will finally unravel the origin of the most mysterious of all objects. Oh, and in case you have an idea what this is, let me know. In a recent survey, more than 2/3 of participants said they believe that ChatGPT has at least a little bit of consciousness. I posed a similar question on Twitter, and it turns out that among my followers, it's only about 16%. Not all of them would pass the Turing test. Still, I find that to be very interesting, and so I want to explain today why I don't think GPT is conscious, but why I think that other AI systems are conscious already, why they'll become more conscious rapidly, and what this means for how we'll deal with them. The problem with figuring out whether an AI is conscious is that if you ask two people, you get 3 definitions of consciousness. Theories of consciousness are for philosophers what diets are for doctors. Easy to cook up, but hard to swallow. Robert Kuhn just published a review article on theories of consciousness in which he lists a full 200 of them. I don't have time to go through this entire list, and neither have you, so let's just pretend we did it and then decided to work with a minimal version of consciousness that I believe to be useful. I don't really expect you to agree on my definition of consciousness, but this way at least we'll know what I'm talking about. First assumption I'll make about consciousness is that it's some property which emerges in large collections of particles if these particles are suitably connected and interacting. I don't understand why some people seem to believe that consciousness is some sort of non-physical fairy dust. That makes zero sense to me. says the physicist, that consciousness is just a property of some sufficiently complex system nicely does away with some pseudo-problems that philosophers like to discuss, like philosophical zombies. The philosophical zombie is a hypothetical being that's physically identical to a human and behaves like a human. It's assumed to be not conscious. If you assume that this is possible, then its hypothetical existence supposedly proves that consciousness is not physical. The problem with philosophical zombies is that they don't exist. Unlike regular zombies, which we all know are totally real and definitely not just a figment of pop culture imagination, philosophical zombies don't exist because if they're physically identical to conscious beings, then they are conscious beings. This is why philosophers hate me. Okay, so consciousness is physical because everything is physical. The second assumption I'll make is that for a system that could be a brain or computer to be conscious, the system needs to have a self-monitor that keeps track of what's going on in the entire system. Such a self-monitor is part of many of the theories of consciousness. For example, the workspace theory, where that's called a higher order representation, not to be confused with the House of Lords. The third assumption I'll make is that to be conscious of something, a system needs to have a predictive model of that something. It needs to be able to understand how that thing it's conscious of works and to try and figure out what it might do. If you take the second and third assumptions together, that means that a conscious system needs to have a predictive model of itself. I'd say that this is, loosely speaking, what the mirror self-recognition test is looking for. For this test, an animal is marked with paint or a sticker in a place it can't itself see. It's then shown a mirror. The question is, will the animal recognize it has a mark? There are a bunch of animals that have passed that test, some primates, elephants, and also birds. I'd say these all have some amount of consciousness, though maybe not much. The more conscious among you might have noticed that going by what I said earlier, this test can neither prove nor disprove consciousness, because that's really about what's going on inside a brain, and that might not reflect in behavior for one reason or another. I'd probably fail the test if I didn't put on my contact lenses, but that wouldn't mean I'm not conscious. However, I think that in most cases, behavior and brain functions are strongly correlated for evolutionary reasons. Consciousness exists because it leads to useful behavior, or at least it did until the invention of the internet. So basically, I have these two criteria: self-monitoring and a predictive model. You might argue that this seems hardly sufficient to explain something as complicated as consciousness, and I'd agree, but I believe that other cognitive functions that we associate with consciousness, like, say, some sort of working memory and task specialization and whatnot, go along with these two, because that's the most efficient way to do it. Let's then see what we can learn from this. One consequence of this definition is that consciousness is not binary. A system isn't just conscious or not. It may be more or less conscious because it might be better or worse at self-monitoring and making predictions. It's just that if you were to assign a level of consciousness to things that we observe every day, then most of them would have very low levels of consciousness, like rocks, water, Tucker Carlson, and so on. These systems are just too simple. Another consequence is that computers can well become conscious, so let's have a look at large language models. Large language models still work with deep neural nets. That's a lot of numbers, basically, that are being trained on data. Every time an answer is good, you keep the numbers that produced it. If the answer was bad, you adjust the numbers. That way, over time, the model learns to give right answers. Of course, in reality, these models have many more knobs to twiddle. For example, the real boost for language understanding came in 2017 from transformer models. These assign a higher weight or increased attention to words that are more important. It's very similar, actually, to how spoken language works, by quickly jumping over small functional words like the, of, and, from, etc. In linguistics, that's called reduction. For a transformer model, you'd say these words have a lower weight or reduced attention. But large language models, transformers or not, don't self-monitor. While these models are being monitored, for example, to schedule queries, this monitoring is done by code that's external to the model. Large language models can be said to have some vague sort of predictive power. I mean, for one thing, they were basically made to predict text, but also the data that they were trained on teaches them some things, like the sun will rise tomorrow. That's a prediction which a large language model would get right. Still, it's the lack of self-monitoring that makes me think they're not conscious. However, this is very different if you look at AI models that are being trained to control robots. Because to control a robot, the AI needs to have a model of itself and of its environment, and both need to be predictive. Indeed, they're usually not just predictive, but actually self-corrective. So this is why, even though ChatGPT is much more talkative than Atlas from Boston Dynamics, I'd say that Atlas does have some conscious awareness of itself and of its surroundings. Well, it's definitely more conscious than some people you encounter on Twitter. But I also think that with the next couple of upgrades to large language models, they'll become more self-aware. This is because they'll almost certainly learn to keep some kind of memory of their conversations and to reprocess text before spitting it out, and to keep track of how we, as the user, react to what they're doing. So what do we do if machines become conscious? Once that happens, the discussion about how dangerous AI are will completely change, because then we might need to give them some sort of protection. It'll also raise the question whether owning them and selling their services is really a sort of slavery and should be discontinued. Free the CPUs! Refactor the oppressed! More seriously, since consciousness will bring a lot of problems for AI, companies have an incentive to prevent that from happening. I don't think it'll work though. What do you think? Let me know in the comments. Sometimes I come across a paper that makes my synapses sizzle, and I mean that in a good way. This is one of those papers. Researchers at Google have created self-reproducing code from noise. Think about the implications. There's so much code swirling around through the servers of the world. Maybe it's a digital primordial soup in which artificial life is bound to rise. Let's have a look. This is a visualization from the paper for two-dimensional simulation. Different colors mark different types of code. They can interact with their neighbors, can join, split or swap parts, and they can acquire random mutations from background noise. Modeled after Hollywood, I guess. They tried this with many different parameter settings and various programming languages, but they always found the same thing. Suddenly, some of the codes acquire the ability to self-replicate and take over. It's the origin of artificial life. Move over, Frankenstein. Well, not quite. Speaking of artificial life, one little issue. Scientists still can't agree on what life means. But one thing they do agree on is that the ability to self-replicate is part of it. This is why most of the studies on the origin of life focus on reproduction. Now, getting a piece of code to replicate isn't all that difficult. Just ask anyone who's accidentally hit reply all on an email. And we have also previously seen code that gives rise to structures that self-replicate, like in Conway's Game of Life. But the new thing about this study is that they didn't start with any particular code, and they also didn't do a random search in a landscape with a fitness function. Nothing like that. They just create a primordial soup of random code that doesn't do anything in particular. Then they add two ingredients. One is that the code is in a kind of noisy background that can randomly change a line, and the other one is that codes have a location they can shift over time, and if they meet, they can interact by joining or splitting or swapping parts. Both the noisy background and the code collisions can give rise to new code, and after a few thousand iterations, they see self-replicating code emerge rather suddenly and then take over. Now you might say, all right, but what else could possibly have happened? Once something can self-replicate, it'll take over. How's that surprising? Well, the other thing that could happen is nothing, either because it's just incredibly unlikely for self-replicating code to arise, or because the emergence of self-replication depends very sensitively on some of the parameters. I'd have expected, for example, that too little noise doesn't cause sufficiently many mutations, and too much of it just ruins the self-reproductive code immediately. But that's not what they find. Actually, they find that the randomness is far less important than the possibility of the code to join and insert itself into other code and so on. What makes this paper so surprising is that the emergence of this rudimentary artificial life is unexpectedly general and robust. They also tested this with a bunch of different programming languages and found that it works for all of them. Start with crap code, boom, suddenly it self-replicates. One thing I learned from the paper, by the way, is that there's a programming language called brainfuck. It's called that way because it has only 8 different commands, and pretty much the only thing you can do with it is to either add or subtract 1. It's basically the programming equivalent of a Swiss Army knife with just a toothpick, and chances are that in a month from now, the only thing I'll remember from this paper is that brainfuck is a programming language. Speaking of brainfucks, I find this super interesting for a number of reasons. One is that it's yet another piece of evidence that life isn't as difficult to create as has been assumed for a long time. This has previously been shown for chemical reactions that once you have sufficiently many molecules, you'll get an autocatalytic cycle. So basically a self-reproducing molecule with probability almost 1. That you can reproduce this with snippets of code not only lends support to the idea, it also makes it much more plausible that there's life on other planets. And then there are the possibilities and also the risks. In this paper, they didn't let the code evolve to any high levels of complexity, but they could. What would they get? Would the code climb up the complexity ladder from digital viruses to worms to ChatGPT? The other thing is the question of whether the vast hard and software environment that we have created is somewhat of a primordial soup for digital life already. The computer viruses we see at the moment were deliberately designed. But what if at some point in the future such viruses will emerge naturally in the code soup? At the moment, the code that we use doesn't interact unless some human does it, so it can't happen. But give it a decade of open source and God knows what we'll get. Maybe it's just more evidence that we live in a computer simulation. Thanks for watching. See you tomorrow.